Welcome to this ATA Insights webinar. Thank you for your ongoing interest and support of our webinar program. Today's session will begin in 2 minutes. ATA Insights Webinars is an online platform for the dissemination of professional renewable energy knowledge across international borders. Our aim is to democratize access to information, for innovation to spread faster, and to make the industry more competitive. And we do this through our online sessions, open to all our members. Every year we do more than 100 sessions with over 250 speakers, 50,000 attendees from more than 50 countries. To participate in the session today, use the chat on the right-hand side to introduce yourself, your company, and where you're joining from. Under the screen, you will find the Q&A box, where you can send your questions for the speakers. We will get to as many as we can today. We're recording this session, and we will send you a link to the materials in a few days. Please consider supporting our content creation for the webinar program. Contact us on the email on screen. Well, good morning, good afternoon, ladies and gentlemen, and welcome to this session where we're going to be talking about concentrated solar power, also known as CSP for friends, and thermal energy storage, a glimpse of future technical innovations looking to improve efficiency and cost competitiveness. As you know, many of you, and I can see the names there, and I can see a lot of friends. I'd like to send a greeting to Fred. Fred Morse, is very good to see you here and to see other old friends that are connected today. Please use the chat to introduce yourselves, your company, and where you are joining from, because we love to see, where you guys are and that you guys are joining. But for those who may be more unfamiliar with CSP, or perhaps you haven't heard so much about it and you haven't been working 40 plus years in the industry like Fred, concentrated solar power is a solar energy that uses the heat of the sun that can be stored and that can produce energy essentially 24/7 or whenever you need it. So it's a bit of like a solar peaker plant, if you like. So it has spinning reserves, has everything that a gas or a coal plant traditionally can do, only that we can do it renewable with no CO2. So it is great. They are really quite competitive, even though, a lot of people still may not have recognized this fact. And we will talk about this, I'm sure, a little bit at some point today. But we have two people today that are actually researching and have been for a number of years, and their companies have been for a number of years on how to make it even more competitive. I'd just like to say that in the span of about 6 gigawatts, CSP has come down by 70+% compared to, yes, 90% of PV, but over a deployment of more than 600 gigawatts. So the difference in deployment is so much larger that it's unsurprising, that the cost will come down that much. So CSP in this way has done really well. However, we're still fighting for it because every cent counts, as we know. So I'd like to ask Tom to please introduce yourself so that people can get to know you.
Hi, Garan. Hi, everybody. My name is Tom Wray, Vice President of Business Development for BrightSource. Been in the energy industry for over 20 years now, and been with BrightSource for 7 years.
Thank you very much, Tom. You are also an industry old-timer, but not yourself an old-timer. Jean-Michel, please, if you could introduce yourself.
Hello, everyone. My name is Jean-Michel Wautelet. I'm a business developer and sales manager for the John Cockrell Renewable. I've been working for the group for more than 13 years now, mostly in technical and in sales since 2017. And I'm in the CSP business since 2016. Nice to meet you all.
Thank you very much, guys. As you can see, you have a wealth of knowledge here today. And the one thing we're going to talk about today is a CSP tower. So we're going to be focusing on this one technology that is actually a little bit more efficient, higher temperatures, but I'll let the experts talk about it. The way it's going to work today is you're going to hear 2 presentations from each of the speakers, and then we'll have time for questions. Okay, they're going to be talking about what they're developing. So your questions, please send them through the Q&A box at the bottom You can use the chat to introduce yourselves, but please, the questions, send them through the Q&A box so we can easily manage them. And without further ado, please, Tom, if you can share your screen. And whilst Tom shares his screen, I'll just remind you that we are recording this session. It will be available and we will send you a link so that you can both watch it again, share it with your colleagues, and also download the materials that you're seeing on screen. Without further ado, please, Tom, go for it.
Thanks, Belen. Thanks, everybody. So today I'd like to, as Belen said, talk about CSP and thermal energy storage in what we've termed the Green Revolution. I'll start with a little introduction of BrightSource and our experience, some of the technology and expertise we have, then define what we consider to be the global energy challenge and how we see CSP fitting in with that global energy challenge, and as I say, what we term the Green Revolution, and then try and draw some conclusions. So a little bit of introduction. BrightSource has been a pioneer in the CSP tower world. We started in 2006. We've got as a technology provider, we've got a world-class solar field control system, and also the optimization and management tools that go with that. Very experienced and proven team with our technology hub, our technology is based in Israel, and our sort of business hub based in UK, where I'm speaking from here today. So just to run through that sort of experience, our first project we finished in 2011, Coralinga, and as you can see, we've been evolving and improving since then through a number of projects, right through to our latest project, which is Redstone in South Africa. And just to touch on those in a little bit more detail, the sort of first major project that BrightSource was involved in was the Ivanpah complex in California, but still the world's largest sort of tower complex. 3 plants, each plant about 130 megawatts. Has each plant has about 60,000 heliostats, and you can see adding up to sort of a total solar field of over 2.6 million square meters of glass. This plant was a steam receiver, so the plant runs from sun up to sun down, and the heliostats were wired. So every heliostat was wired, connected to the central control system and for the solar field. Project was completed in 2013 and it's now been successfully operating for over 8 years. The next sort of evolution was the Ashland plant, built in the Negev Desert in Israel. Some big changes here in that the tower is much higher. You can also see that the plant was around about 121 megawatts, steam receiver still, but you can see here, and it highlights the sort of ability of BrightSource solar field technology to work in unusual areas, and the solar field area here was constrained, and you can see we actually had a dry river running through the sort of top left and the bottom right, straight through the whole solar field. This project has run about sort of 50,000 of our heliostats. The next generation LH 2.4, it was wireless. It reached commercial operation in 2019 and is operating successfully. Then the next step was the NOR project, quite a famous project in Dubai, as many people have heard. Very large solar field here. Over 70,000 of our latest generation LH 2.5 heliostats, each 25 square meters. And this project is molten salt, so 15-hour storage. So the plant's operating from sort of 4 p.m. at night right the way through to night to sort of 10 a.m. the next day. And interestingly, I think a lot of people, it was well publicized at the time, this was one of the big triumphs of sort of the CSP, a world record-breaking tariff when it was bid and publicized at $73 a megawatt hour. Then the last project I was going to talk about was Redstone in South Africa. BrightSource was awarded this project last year. Again, using our latest LH 2.5 heliostat, 100 megawatt plant. This plant operates from sunup to 11 o'clock at night and has 12 hours of storage using molten salt storage technology.
Are you okay? Yeah, correct.
Yep. Okay, so just moving on now for a little bit about BrightSource's expertise and and technology. Really, I'd like to talk about sort of 6 things. Firstly, at the start of a project, how do you optimize the solar field layout to make it most efficient, most competitive? And Brightsource has specific technology for that. The actual design of the heliostat itself, the whole wireless concept, coatings for the receiver to make sure that the energy we actually send to that receiver is absorbed in the most efficient way. And then the control system, a bespoke control system to control the solar field to make sure that we are maximizing the amount of energy we deliver to the receiver, but without overstepping any of the key limits. So again, very important. And then lastly, generation and weather and generation forecast, which I think is coming more to the fore as plants try to optimize, so try to predict short-term and long-term, what's the weather going to be and what's the best time to run, how you can do that. So just looking that in a little bit more detail, in terms of solar field layout, several of our competitors just put their heliostats in rings and patterns, whereas Brightsource actually has specific technology, specific algorithm, which aims to sort of place the heliostats in the optimum position, given the terrain, solar field height. And the objective, you can see the picture on the right, is that, so from the receiver's perspective, you're seeing just a continuous sheet of glass, no blocking, no shadowing, no gaps. So you've got the most reflective area in the smallest possible space to get the maximum amount of energy onto the receiver. Secondly, in terms of, I mentioned before, wireless, here we have a picture of our latest LH2.5 heliostat. This is a wireless heliostat, and the way this works, we have masts within the solar field, and those masts communicate wirelessly to an individual group of heliostats. This way we can have a full 100% redundancy, but we greatly reduce the amount of cabling and connection costs associated with controlling the solar field. Lastly, the heliostat itself. There's a number of sort of theories on heliostats. Some people have gone for large ones, 150 square meters. We've stuck with a small heliostat, around about 25 square meters. Particularly, we made this smart, autonomous, self-tracking and self-powered. No requirement for any third-party power. All runs off its own small control module with its own battery power. High aiming accuracy, and easy to install. And you can see here, there's no need for sort of trenching, leveling, anything complicated. We can take the ground as it is, and we can build on it. So just moving now from a little bit more, what do we see as a global energy challenge facing us? And I think to date, there's been a huge amount of PV and wind installed around the world, but that installation has been able to rely on fossil fuel backup. And that's really avoided the need for renewables to have to work overnight. However, I think recently the COP26 and the recent climate change commitments, we're going to see a huge increase in renewables. We see a further decrease in old fossil fuel plant retirements. We see the birth of green hydrogen and the production of green fuels requiring electricity. Electric vehicles, again, set for a huge increase in growth, and generally the decarbonization of industry, which up to now has probably lagged behind the electrification. So we think all these factors are going to lead to a big need for storage, a big need for additional grid management, and certainly some backup standby generation to balance some of these intermittents. Just a point on the standby generation. Many people sort of talk about how gas-fired generation is a great transition fuel, and the gas plant at the moment does provide a lot of the sort of overnight stability. But I think as we've seen, gas is low carbon, it's not green. And as we've seen in Europe, and we've all experienced in Europe in sort of recent months, the price of gas can be extremely volatile. And certainly, if you look at a couple of graphs we pulled out, gas pricing, power prices in Europe now are over sort of $200 a megawatt hour. Not only that, there's also the risk that the gas is probably being imported. So you're a little bit of a victim of sort of international politics. So in summary, as we see this global energy challenge, large increase in renewables required to meet the country's commitments, real need to manage intermittency, and make sure we have good stability. So all types of storage will be key. Just a few sort of stats at the bottom there, the amount of wind, PV and solar and electric vehicles which are expected sort of introduced in the coming years up to 2030. This is all courtesy of Bloomberg New Energy Stats. And then on the right here, the amount of storage which is expected to be installed. And just to put that into sort of context in the CSP world, if we think of the amount of storage there, it's something like 250 gigawatt hours a year. That amount of storage is the equivalent of building 200 normal energy plants, with 100 megawatts with their 15-hour storage, 200 per year. Now, no one's saying that's going to happen, but I think it illustrates the size of the challenge we're facing. So with that overlay, how can CSP play in this market? And so firstly, to sort of explore that, what are the benefits of CSP? So certainly it is one of the few controllable, dispatchable, renewable technologies. When we combine that with molten salt storage, it provides a form of low-cost duration storage, ideal for sort of overnight applications. It can be hybridized with PV, hybridized with batteries to provide firm baseload or load following. And I think, as you mentioned, Belen, because CSP has the traditional turbine generator, it provides them full range of synchronous generation, a full range of ancillary services. And one issue we think is quite important here is it complements PV in terms of increasing grid utilization. With the huge increase in demand for renewables, you can see that the grid is struggling. And in several countries, grid issues are now becoming to the fore. And if you put a grid and you've just got PV on the grid, you're probably only utilizing that grid 20% of the time. So adding CSP certainly allows you to increase that utilization. And then from a system perspective, it's reducing the costs on the transmission side, the sort of system. So in terms of storage as well, that obviously several ways people can store electricity, potential, chemical, thermal, mechanical devices. And all these technologies have a sort of different sweet spot in their durations from the very short term to the minutes to sort of 2 months. CSP and molten salt storage is ideal in this sort of 10 to 20 hour range. So it's proven, very well proven in several years now, reliable, long operating lives, 30 years plus. And it's certainly, it's very much sustainable compared with certain issues with batteries and the use of rare earth materials. How do you dispose of a battery at the end of its life, which is much shorter? Here with molten salt, it's stable and there are no sort of supply chain sustainability issues like that. And then lastly, a couple of in sort of third world or developing countries where local content requirements are very important and local job creation, CSP scores very highly on providing those criteria. In terms of cost competitive, Belen, you mentioned again sort of CSP. I would argue that CSP with TES in that sort of its niche for overnight is certainly cost competitive. I would argue it's cost leading, sort of cost leading technology for that overnight storage. So a couple of examples here just to share, and this really is the Northern Energy example where you can see how you've got the PV operating in the day, you've got the CSP operating overnight to give a sort of hybrid solution which reduces the overall cost when you blend the CSP and PV cost. And as I mentioned before, increasing grid utilization from something like 20% if it was just a PV up to sort of 90% for the combined plant. Here with a bit of a further tweak, adding a sort of some batteries to sort of cancel out short-term intermittency during cloud events during the day. Very helpful here if you were looking for off-grid applications, something requiring continuous operation, maybe in production of green hydrogen in an off-grid location. So in some developments in the future, certainly we see future performance improvements, and Jean-Michel will talk a little bit about that, particularly around the storage side, different materials, high temperatures. I see as more and more CSP gets installed, a greater ability to standardize. And standardization clearly brings a number of benefits in reduced construction times and repeatability. Certainly on moving down the scale in terms for industrial scale, I mentioned the decarbonisation of industry, moving to almost sort of modular concepts for use on industrial scale. We think the hybrid model will continue with both PV and batteries, and this in turn will give us the continue some cost reductions. You mentioned, I think before, Belania, there's big cost reductions being achieved to date on PV from a huge installed capacity. There's about 6 gigawatts of CSP installed in the world. And as you said, looking at the numbers, we've achieved sort of cost reductions in the 60% to 70% range. So I think it's pretty impressive. Picking up on the energy point and the grid point, certainly now we see this in China, where a lot of wind and PV capacity is stranded. They cannot get that power away because of the grid's instability issue, or some grid limitation issues, and the ability to put some CSP with storage. You can store that energy and then release it at a more appropriate time. Green fuel production, we talked about, I think it's hydrogen, ammonia. Certainly, if you look at how do those production facilities sort of increase their production hours, aiming to run 24 hours a day, something like CSP, key to be part of the mix there. Then lastly, on the sort of more on the control side, I think improved system control, weather forecast and prediction, again, all aimed at this future world where the grid is going to have to be managed a lot more precisely. So how do you control the dispatch of the plant? How do you optimize that system? So overall, you manage to get your energy where you need it. Having said that, what do I see as the key challenges we're facing? And I think one of them for CSP is all around power bid design and regulation. If a bid comes out for electricity and they just say we want LCOE wins, clearly the winner is going to be PV. It's the lowest form of renewable, but things have to be a bit more sophisticated. Up to now, that's been a very successful strategy, but up to now things have to be a bit more tailored to what is actually required. And you're starting to see auctions come out where they're looking for overnight capacity. They're looking and they're recognizing some of the benefits of CSP. So I think as an industry, one of the things we really have to work on is showing the benefits of CSP and why people should be tailoring their bids to allow CSP to compete. Then the last point I think is a wider uptake in the developer community. CSP is a more complicated animal than PV, so it takes a bit more to understand it. But I think again, one of the things is to get more developers and more industry players to be willing to take on projects and develop some projects. So in sort of conclusion, the world's going to decarbonize. They've got tough climate change targets to meet, and this is going to see a huge increase in intermittent generation. This in turn will drive this big need for storage, enhancement management, and how you're going to back that up. We think all types of storage are going to be essential, and certainly batteries are going to be there, and we think CSP is going to be there. It's one of the few forms of dispatchable renewables, and when you add it to with the CSP and the storage and the blend, we think it's a great solution for overnight generation. It's cost competitive, and as I said, it can be hybridized with other plants to reduce overall system costs and increase grid utilization. Thank you very much.
Thank you very much, Tom. It's been a great presentation. You went through so many issues and you had a lot of numbers, which I'm sure that everyone will appreciate. So thank you for your presentation. You have a bunch of questions that you know. You can either start reading them or we'll read them after live. I'm going to ask you to stop sharing. And for the person who asked the question, we will have the materials and the recordings available for you later. So we'll send you links. Don't worry, you'll have the chance to study the numbers. But also send questions. You have Tom here, you have Jean-Michel here. You can ask the questions and hopefully and for sure they'll be answered. So Jean-Michel, if you can please share your screen and give us the presentation, that'll be great. There we go. And yeah, the numbers are very clear. The deployment of PV is 100 times more than of CSP. The cost reductions are not 100 times more. Just saying. Anyway, go for it.
Okay, so everyone Hello, I could see several people I know in the list of attendants, so hi to you. So I'm gonna present the part for John Cockerill, but before that, as I have such a wide audience, I thought it would be a good idea to talk about me personally. I was born in the 80s, and I have always dreamt about building and designing giant robots, like these guys. I found that online. It's in China. Basically, they're building life-size transformers, and I think that's awesome. And that was I was dreaming about when I was a kid. But actually, I'm happy to see that I have done better than that. I'm working for a company that is building solar receivers for solar towers. And when you're considering this, I mean, a solar tower is at 260 meters high. That's close to the Eiffel Tower. And when you're looking on the right, you're seeing the size of a solar receiver compared to a regular guy like me. So it's huge. We're talking about several thousand tons of steel and tons of different materials and complexity on top of that tower. And that is receiving close to 1,000 times the amount of energy that is falling on the ground. So it's a huge piece of engineering. So actually, is it better than transformers? Nah, I wouldn't think so. But basically, it's close to it. So I'm going to stop talking about transformers because my management asked me to. And I'm going to just switch to the rest of my presentation, which is basically our company first, which is a company that was there at the start of the Industrial Revolution. It has 200 years of history in various fields of engineering. More specifically, I'm working for the renewables part, which is with solar thermal, which is our topic today, but also in green hydrogen, and in a department IRS that is focused on PV and electrical batteries. So that we're actually covering the global, let's say, spectrum of these new renewable technology. So as I said, we're suppliers of molten salt equipment for CSP plants. So that's a quick schematic that I'm sure most of you know about the general principle of a solar tower. And you can see that in red, this is the equipment that we're specialized on, especially the solar receivers, which I'm proud to say that we're currently the world leader in supply of these equipments. So as you can see, what is very interesting, and as Tom said, is about the storage capacity. You can clearly see the thermal energy storage tank there that are storing the energy in molten salt. A few references quickly, because I just can't resist to show you beautiful pictures. Our first one was in South Africa. Key Solar 1 was in steam. Second one was Cerro Dominador in Chile, which is in operation right now. You could see that was also a beautiful system that was allowing to erect the receiver on the ground and then lift it up in one piece. You could see on the picture there. Then Haishi in China. That was the first actually Western receiver in China and the only one so far. Of course, Dubai. I don't need to introduce it to you. And finally, Redstone, which we're happy to work with BrightSource on this great project. Now, a quick round the clock about why CSP. So Tom told you about a lot of advantages about CSP. Of course, it can be 24 hours 7. It uses large-scale storage, so it helps with frequency regulation with, of course, no CO2 emission. It doesn't use rare earth or special minerals that would be used in electrical batteries, for example, or on PV. So it has many, many advantages compared to other renewable technology, and it's actually complementary to them, as Tom said. Where would you put actually a CSP plant? That's kind of interesting to know. So we're using what we call the DNI, which is direct normal irradiation, which is basically the amount of solar energy that is falling on the ground. So as you can see, starting from 1,800 kilowatt hour per square meter, and you can see it starting in yellow, this is roughly the areas in the world where CSP becomes really interesting economically. Unfortunately, I can't have a solar tower in Belgium, where our headquarters are. But once you get into Spain, North of Africa, Middle East, Australia, South of Africa, Chile, Western America, you can see that the CSP is really interesting. And that's actually where the big projects are for the moment. South Africa, Chile, there was a big boom in the United States. There was a big boom in Spain, and we're hoping there will be a new big boom very soon. So this is just to give you this overview. Also about dispatchability, Tom discussed a lot about this need for dispatchability, and I wanted to share what we call the duck curve that has become widely known among in the CSP business. Just to give you this view, this is from California, the different megawatt, and you can see from 2012 to 2020, between let's say 9 a.m. to 4 p.m., the amount of PV that is actually helping the grid. So you can see that it's curving. So that's very good. But what's very interesting is to see, starting at 5 p.m., the need for power when people go back to their homes and turn on their television and everything. You have a huge need of power that PV cannot actually give, because PV is just working during daytime. And for this huge ramp up between, let's say, 5 p.m. and 9 p.m., you need alternative sources. So either you can have fossil-based electricity, or you store renewable energy. And this is where storage becomes so interesting. So the basic idea here is to know that you can't really have standard PV or wind, because, well, it will require sometimes to be stored. So there is a need for hybridization. CSP and thermal storage, there is a perfect fit for several industries. What you can see here in the map that you know very well right now for the DNI, it's a fit for the mining industry. You can see that the big mining industries in Chile, South Africa, Australia, North of Africa, there are also the same areas where the DNI is good for CSP. So that's a very good place to use CSP, and especially CSP can be used also in off-grid applications, which is perfect for mining. The second point is green hydrogen. Green hydrogen basically needs baseload electricity to produce, in an economical way, green hydrogen. And this is what CSP can offer. CSP can offer baseload 24/7. So that's a perfect fit for hydrogen as well. And the third point is green heat. Now, the industry will need green heat as well, as much as green electricity. But green heat is quite difficult to produce. If you just take out the fossil fuel, it's quite kind of difficult to make green heat with PV panels or windmills. In that, CSP can help too, because basically we're producing steam. And so if we can produce green electricity with green steam, we can just produce green steam and feed industrial processes. A quick word about numbers, about LCOE, which is also a big topic among the energy industry. If you're looking at PV, pure PV today in 2022, the LCOE is reaching $20 per megawatt hour. So it's very low. And people always say, well, yeah, you see, PV is much cheaper. Of course it is, but there is no storage. And you could see with the duck curve where storage is needed. If you're looking at the latest numbers for CSP and PV, so hybridized plants, you could see that DWAR in 2018 reached $73 per megawatt hour. And you could see the hybridization here, 700 megawatt CSP and 200 megawatt PV. And the groundbreaking price of the Licana bid in Chile, that reached $34 per megawatt hour, which is just groundbreaking. And it's showing that it's just getting close to pure PV, but with a huge amount of storage in it. So main message here is hybrid plants are the future. Now, a word on energy storage. I wanted to share with you this these data from the DOE in the United States, showing the share, the worldwide share of storage in the world by technology. And you can see that the molten salt thermal storage is clearly the leading storage of energy. You can see lithium-ion battery is the second, way behind. You have hydrogen storage that is nearly non-existent. So this here shows that molten salt is already a mature technology to store energy. And then you have this emerging technology for power to heat. And this is very interesting to combine it with PV and wind, also in areas where you don't have the DNI necessary for a CSP plant. Because if you're looking at this chart, if you have PV or wind, you can transfer this electricity, green electricity, into heat using electrical heaters. Use the tanks that we use in CSP to store this energy in heat, just like in a CSP plant. And then to reuse this heat using steam generators to produce either green electricity if you have a steam turbine, or produce green steam. So basically, in any part of the world where you have green electricity that you could use to produce heat, you can use this kind of system. And one case study is about the coal plant conversion. So in Germany, for example, you've heard that there will be a lot of coal power plant to be converted, or at least to be shut down. Just let's imagine if you just delete the coal-fired boiler and you keep the Rankine cycle, you keep the steam turbine, you keep the BOP, you keep everything that is costly, actually, it's there, can be reused. And you add these electrical heaters, the tanks, and the steam generator that would feed the steam to the steam turbine. That means that you get a hub that could absorb any green and intermittent electricity peak on the network, or can absorb any new renewable electricity that will be added to the grid. And we've studied this system, and we believe this is the best solution to answer the coal power plant's transition challenge. And finally, I will finish by a quick word about the future developments, the future of CSP that we're working on. One of the first things is about switching to solid particles. Why? It's because we would like to go higher in temperature. We're already studying new molten salt that could go, well, new types of fluids that could go up to 850 degrees. But solid particles allow us to go up to 1000 degrees, which could be very useful for some industries, for example. Also, we're investigating solid thermal storage. So using, well, a lot of different ways of storing heat, which we believe will be the future of the industry. And finally, once you get to 1000 degrees, you can use supercritical CO2 in your power cycle, which also increase efficiency and just take you to the next level. So that's it. I thank you for your attention. And well, if you have any renewable challenge, please come to me. I will get a bonus for that. Thanks.
Thank you very much, Jean-Michel. And I agree, you know, like CSP plants are way cooler than transformers. But I'm glad you talked about transformers because it's such a cool engineering thing. Some really interesting slides that you had too. I mean, those slides on the cost, there is a lot of questions about that in here. Many of which we cannot answer maybe straight how they've been asked, but you get an idea of, you know, LCOE if you run the numbers essentially. Anyway, let's start with the questions. We have about 20 minutes, so we can answer some of them. The first is for Tom, a few questions, but I think I'd like to open them to both of you if, you know, there is anything else you want to add. One is, what is the system efficiency of the solar concentrators? From the ratio of area to megawatt, it appears to be about 20%. Tom.
Sorry, I mean, overall system efficiency of 20% is a reasonable number from sun in to electricity out the door.
Oh, I see. Okay, so
I think
it's
that's
about
the question,
right. Okay, how many losses can you expect in the storage tower in subsequent conversion? They're very specific. You can take a look at them if you like.
I think we'd have to answer that with a bit more sort of information rather than just, I don't really understand the question.
Okay, so let's pass this. And they ask you this one is very specific. What the wireless technology is used for your heliostat control?
Sorry?
What wireless technology is used for your heliostat control?
It's our own wireless technology, our own design, using a commercial frequencies.
Okay. We discussed costs, so I'm going to put this question. And there was a question here also about the minimum temperature that the salt tower can accept. I don't know. I mean, I know the salt has a minimum temperature, but I don't know about the tower. So I'll let you guys respond this. Is the one at the top?
Well, basically, molten salt minimum temperature is around 290 or 300 degrees. So that's the average number. I don't know, Tom, if you want to complement this.
Yeah, no, that's it. And the key thing is the delta T. And what Jean-Michel was trying to say, the bigger the delta T, the better. So hence the drive to go for materials that can have a higher top end temperature.
And today, like most towers operate around the 575, is that right?
565, right. Yeah.
65. Okay, essentially. So you take that into consideration, and you can never go lower than 230 to 240 with the salts.
No, otherwise it would become solid.
Exactly.
So that's the trick. And the research that we're doing right now is to increase 565 to 850, and then moving forward to 1000 with solid particles. It's all about efficiency. The higher you go in temperature, the more efficiency you get. So
actually, if we broke, up a little bit more, just a little jump, it would make a huge difference to the LCOE. So sometimes, with a little jump, it doesn't look like much, but it makes a huge difference. How can the salts from the thermal storage be used after the lifetime of the plants? What do you do with them after you finish the plant? And I think there is a misunderstanding that this is lithium batteries, like the salts, they don't get damaged. You just they're like the first day, right? I mean, I don't know what you do with them. You can recycle them into another plant, or you can sell them as fertilizer, or what would be your answer there?
I think a couple of things. You could reuse them because the salt's not degrading. So you could either return it to solid state and return it, or you could look to reuse it in another project.
So this is it, guys. There is no maximum amount of cycles in salts. Like, you can use them forever. So as long as you maintain your plant, it can keep working, essentially. Some of the sex plants have been working for 35 plus years.
Yeah, and also the fact is, it is good to know that the molten salt are in itself not a toxic product or anything. Can be used, or could be reused as fertilizers as well. So it doesn't pose the same questions as lithium batteries, for example, that will need a recycling industry behind it. It simplifies this question.
Yeah, I mean, if you went just by this measure, you would definitely go for this technology, because it doesn't give you any waste whatsoever, no problems at the end of the cycle, anything like that. Okay.
Exactly. I think just a word on that. It's really interesting to really see the different storage zones. Actually, if you're thinking about, let's say, small scale storage, it's obvious that the electrical batteries will be interesting. But if you're looking at large scale storage, it's obvious that CSP or thermal storage has really a role to play.
Excellent, thank you. Where would you estimate the solar field technology cost is in respect to the sunshot goal of 50 to 70 US dollars megawatt square meter square? Sorry.
Yeah, I mean, interesting question. I think we're getting there towards that goal. I think that was a 230 goal, if I remember. And I would say now that we are sort of around about the 100 or pushing below the 100 mark. But again, you know, a lot of variables depending on the size of the solar field, the size of the plant, number of plants, but that's the range we're in.
You want to add anything, Jean-Michel?
No, I think Thomas, very clear.
Perfect. And okay, this one is a good one, actually. Can you share your experience in cleaning these thousands of mirrors?
Oh, Tom does it himself.
He starts, and then by the time he finishes, he has to start again. Go on then.
No, I mean, there's a number of this is quite a big topic, but different parts of the world have different cleaning requirements. And for example, that the plants in the iron power plant, the sort of cleaning requirement is very low, maybe 2, 3, 4 times a year. Every time it rains, you also get a free clean. So you can go from a situation where you have very low cleaning requirements to a situation where you need more cleaning, depending on the climate. Up to now, there's been a number of ways to do this, ranging from sort of simple manual cleaning, and it's something that Brightsource is looking at now, is developing that with different forms of more mechanized cleaning. And so it really depends on the situation, what method you choose to optimize how to do it.
I'd like to say something here, and is that, and I suppose this is also a comment for both of you. There are really 2 approaches to this heliostat thing. Either you make the huge and very, very tall, and I'm talking about like the 180 meter square types. Like if you can imagine a dog next to a tree, this is how you would look in height next to the heliostat, because it's so large. And then this is the second approach, which is they're much smaller, they're much lower, but there are also many more of them. So there is like the 2 approaches. I don't think this is the forum to discuss which one is best, because these 2 guys have a very clear, you know, understanding of what is the best setup. But what is true is that yes, you have more of them, but can you imagine cleaning something that is 10, 12 meters up high and there is 180 meters squares, like when to get to the center compared to a much smaller mirror, which is much lower, you know? So even though there are less of them, sometimes when you're looking at certain issues, you know, you might find that actually, I don't know. I mean, I don't have the answers. I'm just saying there's a lot of things to consider, you know, when looking at this. And yes, there is thousands upon thousands of mirrors, but also, you know, they're a lot more reachable, I suppose. And
yeah, it's simpler. It's simpler, and you can do it. You can do it, you know, from almost a manual approach. If
right.
It's more heliostat. That is still the case.
Yeah, thank you. So I just wanted to make sure that this was understood, because there's a huge difference. You know, if you want any of the other plants, you can see that they're like humongous. Okay, so next one is there an efficiency guide for the different storage mechanisms when combined with CSP at different scales? I don't understand this question. Is there an efficiency guide for the different storage mechanisms with combined with CSP at different scales? Is he talking about hybridizing?
Maybe the question is to know whether there is a gain of efficiency where you scale up the plants, whether it's better to have a 50 megawatt, 100 or 200 megawatt plant to increase the efficiency. I think this. Do
you want to answer that question? Because for towers it's quite clear, isn't it? Okay, someone. Well, yes, hybridizing. Yeah.
For hybridizing, yes, I think it's always like a special case study, actually, because it depends on many different factors, like the DNI, as I said, the air purity. I believe there is a sweet spot into the scale of the towers. For the moment, I think we have, and I will let Tom correct me if I'm wrong, but we're just in 50 megawatt or 100 megawatt solar towers, and I think this is now reaching the sweet spot, sometimes a bit higher than 100, maybe 120, 130. But there are some limits. I mean, you couldn't go 200 megawatt with the same amount of storage, because I mean, you reach some limitation about the solar field size and the distance between the mirrors from the tower, and the air and the light will become scattered a bit too much. for the moment, I would say the sweet spot of the industry, 100 megawatts. But okay, I will let Tom correct me.
Well, I think that's broadly right, Jean-Michel. I say it depends on DNI. Places like Chile, certainly you can go a lot larger because of the great DNI. But there does become a point where you've filled the ground with your solar field, and adding more heliostats is not getting you any more energy because of the distance to the town is so great, and that's kind of the limit. So, as Jean-Michel said, it depends on where you are, what the DNI is, kind of sets the optimum size.
There's also something to consider in terms of
150 is where the industry is now.
Okay, most projects now, they hybridize with other technologies like PV for parasitic consumption as well as other things. Yeah. You know, why use, you know, the energy from the tower that you can actually use at night, you know, and use in other times. Honestly, you don't really need it in the daytime. You know, like you could produce energy in the daytime with something else, but at nighttime and in the periods where, you know, you don't have that great resource, but you have a lot of demand, that's the right time for this technology.
Exactly. And also it's important to point out that the power auctions that are sometimes in several countries, that what Tom was saying, they're sometimes not really addressing this point about when the country needs the electricity. Because if we're just looking to the cheapest renewable electricity, of course, PV and wind will come first. If you don't ask specifically some storage features for the plants. And this is where also you have to look at efficiency. Obviously, you have to look at the return, and this is what investors will look like. But I think now, well, for really the investors right now, it would be really interesting to see themselves in 10 years. Right now, the storage needs are just become apparent. In 10 years, I guess that storage will be really important, and investing right now in plants that can provide electricity during the night, it could be a very good investment, because right now this is not really integrated in many companies, in many states, in many ministries. But in 10 years, it will become really apparent, because the more and more intermittent renewable will come online on the grid, the more the duck curve problem will become apparent. And this is where storage will become crucial.
Yeah, very good
that's
point
the sort of holistic thinking, not just thinking, how can I buy the cheapest megawatt? What's best overall in the longer term? And taking into account the, as we said, overnight, the storage, the grid requirements. You know, I think this is the point we're trying to make about taking a bigger view on these bids and the sort of system requirements.
Thank you very much. I think it's important that we understand that is something that we keep on talking about. You know, us in CSP, we've been talking about paying for grid services for a decade, and now the battery guys are helping us make the same. Because the reality is, the minute that you take the spinning reserves and the gas out, you are done. You know, if you have to, you know, PV doesn't work at night, guys. It does not. And then that is where, you know, what you need is like very cheap energy when you have it, and then a little bit more expensive energy when you have it, and, you know, sustainable renewable energy also at night. Anyway, question here about water, you know, and it's asked differently, but I just wonder, how do you source the water? How much water do you need? And how do you cool these plants? Guys?
Actually, the water, most of the plants are air cooled. So on the steam turbine side, it's air cooling. So the water needs are quite limited in terms of water for your steam cycle only, and water for heliostat cleaning, which I mentioned before. It really depends on where you are, how much cleaning you require, but it's certainly something we're very conscious of, and looking at cleaning methods which actually have that sort of minimum amount of water usage.
Thank you. There is here a very interesting question, actually, that I think we should consider. What happens when the salts freeze? How do you deal with that?
Yeah.
You basically don't let it happen. That's the first rule.
You don't let it happen. You don't let it happen.
Yeah, it's
that question. I mean, a lot of the plants have trace heat. Jean-Michel, a lot of plants have trace heating, so you've got protection to make sure that doesn't happen.
Exactly. I was about to say the whole system is actually protected against a lot of different things that could happen. For example, we also have an infrared camera system that is constantly monitoring the receiver from the solar field in order to detect also the hotspots and the different variation of temperature. Everything is heat traced also, so it's maintained with electrical wires to be at the right temperature, and everything is designed with the flows and everything in order never to reach freezing. But furthermore, just in case there would be a problem, just suppose that we stop having energy from the mirrors. Also, we have an extremely efficient design for draining the receivers, so as just with gravity, that the salt would just go out of the receiver extremely quickly, so that there wouldn't be a freezing also that would damage the equipment. So there's been a lot of thoughts behind protecting the equipment against freezing.
Thank you very much. But basically, it is avoided, right? I mean, at the end of the day, if you reheat it, it's going to melt back down, but it's going to take you a lot of energy to do that. So you need to be preparing, and like that is the part of the operation of the plant, essentially. It says here, have you experienced corrosion when dealing with high temperature?
Yeah, I mean, corrosion is actually one of the central research that we've done for the last 10 years, actually. So we spent hundreds of hours and reading everything that the literature had about the different metals that we're using. So we have a know-how now about what the best metals are, the best welding procedures, and we're using, I mean, this knowledge and the practical knowledge that we're having in order to design the system with the best metals and the best alloys that we're using. And also, we're continuously testing in labs samples of these metals to find new materials that could be better, but also to check for the corrosion for the complete lifetime of the plant. Just to give you an example, the tubes of the receiver, which are the best, let's say the most, let's say, a critical part of the exchangers, are made with a highly specific alloy that we've studied that is resisting corrosion at very high temperature.
So it is an issue they need to worry about, but it's not unsurmountable, no? This is what I'm understanding here.
Yeah, well, worry is a big word. I mean, it's a clear issue that we have considered and studied a lot, because this is something very important to take into account when you're dealing with molten salt at 565 degrees. Corrosion is something very important to take into account. This is why you need to study it a lot and to choose the best materials actually for your system. It's always a question about quality versus price. So what we've chosen actually to investigate to take really the best quality, because if you're looking at the tower plant, which is, I mean, a huge investment. We're talking about $800 million for one plant, so that's a big investment. The receiver is a small part of it. But if the receiver has a problem, the plant is down and there is no redundancy for this. So this is why we have decided to go really on high quality to be able to ensure that during the complete lifetime of the plant, there wouldn't be any problems linked to corrosion or otherwise.
Thank you very much. And I have to say also that this technology has been operating for many years now. One of the plants, actually, Juan Ignacio Burgaleta here was referring to a plant in Spain called Gema Solar. Yep. That Juan Ignacio, you say here whether we mentioned it before, and I think we actually refer to the projects that BrightSource and John Cockerill have been involved in. So I don't think we actually mentioned this plant, but this is a different type of project, but a tower project has been operating for like way more than a decade now. So when you see these things, you also have learned a lot of really valuable lessons, and you know a lot about how materials operate, like, you know, what issues are and what issues aren't, essentially. So we're going to take a couple of questions more and then we'll call it a day, because, you know, we're getting to the hour. And one of them is asking you about improvements regarding the reinforcement of the steel stability used for MS tank and pipes. from Danny Q, which is lower down. What improvements can you tell us regarding the reinforcement of the steel stability used for the MS tanks and the molten salt tanks and pipes?
Okay.
Anything to add here?
Unfortunately, this is a bit out of my area of expertise, as we're mostly focused on the solar receiver and steam generators. I know there's been some problems with tanks that had leakages and problems. Unfortunately, I'm not comfortable in answering that. We're not covering this scope of supply.
Same, right, Tom?
Same, yeah.
Okay. There are other people who can answer this question, but we don't always have, the experts on everything. They both know way more than I do or that you do probably about this, but we're not all specialists in everything. What do you believe would be the best way to value the dispatchability of CSP plants? For example, time-dependent PPAs or capacity backups for some gas view of value. So how would you, essentially he's asking you, how would you regulate or how would you make the rules, so that this dispatchability ability could be like paid for and valued?
And I think there's a number of approaches being tried here. In Chile, I think they defined overnight blocks. So that's a sort of simple way to say we want an overnight block of power. I think the issue there is to make sure that as well as saying I want an overnight block of power, there's some sort of measure of predictability. Because in theory you could I've got an overnight block of power, I'm just going to use some wind, but it may not blow. So it's got to be you've got to sort of specify that you want a firm block of power and make sure that those rules are clear. So you get what you want. The other way, as you said, is a sort of capacity payment mechanism that gives you a payment for being available, and then you can generate as the grid requires overnight. If you bid on a capacity payment for an overnight block, again, I think that's a good way under a PPA. So there was a number of ways it's been done, a number of mechanisms. I think the other thing, just to gets it more complicated, but looking at the sort of system costs as well, in terms of the amount of grid cost that's required and making sure that's factored in. Typically it's not, and sometimes that can be detrimental.
Yeah, I think just to complement what Tom said, I think it would be really interesting for all the states, the ministries, to really consider the slots where CSP could help during nighttime, during integration. It's really about having a holistic view about CSP. It's really looking mid to long term rather than short term. I think this is the right time to do it.
Yeah, I would like to add to that actually it is before that it was quite straightforward. You had a demand, and then essentially you generated whatever to fill the demand. That was it. You could generate it anytime. It was very simple, really. If you think about an axis, it was just literally you just had two things to consider, demand and supply. But now you have to consider resource. So the whole algorithm is a lot different, and the way that we integrated renewables up until now has been in the same fashion that we used to do it before. Like, okay, give me power. But PV and wind, really, they give you power whenever it's available. It's just not always available. So then you have to think, what resource do I have, and how can I use that resource to plug the gaps so that I actually have control over what's produced? And the minute that you take fossil fuels out of the equation, you now have a much more complicated formula, or you're looking at it in four quadrants instead of two. So it's a lot more complicated, but it's actually something that can be resolved pretty easily once you consider everything as a whole. So even though it might be much better to sometimes plug in a little bit of storage, rather than continuing adding PV just for the sake of it. And, other issues, like people who know about the grid and grid management know a lot more about it. And we are still missing that. Like most of the tenders I see today, they're still like very technology specific. We're looking for blah, blah. I don't really see a lot of like technology agnostic tenders, although This can also be a hindrance because, for example, in the case of Chile, they did call for capacity overnight, but this capacity overnight was then won by a very cheap bid by a PV plant, which is like, okay, but PV doesn't work at night.
Which is why I made the point about specifying that you can be available and not allowing people to play a game to say, well,
speculation, right? Because
exactly why, exactly correct.
But each market works differently, so it really depends. You know what each market does it like. In Chile makes sense because of the way that they've always procured, their energy. In any case, I hope to see a lot more of off-taking profiles also in the future, because only looking at it that way, like when do I need it and when do I not have it, you get to a situation where you can really start making the calculations as to what's best for the whole system. And that's it for today. Thank you very much, guys. I wanted to ask you whether you think that really hydrogen and renewable hydrogen is going to give us a new sort of breath of life. We're going to see a lot of projects for that, or for power to X, say, because those are really, they're Harvard Bosch. They require 24/7. And if you're renewable, then you need to be renewable. You can't just burn gas to create methanol. Do you see that in the midterm?
Well, I think definitely green hydrogen right now is one of the leading forces also for the renewable industries. I mean, it allows also to be also a kind of storage for intermittent electricity to be transformed into hydrogen. And this hydrogen can be moved and exported and go into pipeline, natural gas, or go into boats and be imported and exported. So it's a new vector, actually. It's a kind of a new revolution in the renewable industries. And as we're part of it with our department, John Cockerill Hydrogen, we're really seeing this demand and this interest to be a huge new green wave, let's say, on the industry. Yes.
I certainly hope so. Thank you very much, Tom. Thank you very much, Jean-Michel. It's great to see you again. And thank you very much for coming and sharing. And thank you all who've been there in the audience. Delighted to be here and to talk about these issues. And I hope to see, that more plants come to the fore, as now in the last few months, we had like the Redstone project in South Africa, a new one in Chile, also very, very competitive. And I hope to see more because in the more deployment, we're also going to see more competitiveness. So thank you very much, and we'll see you next time. Bye.